Welcome back to ECE 340. Thank you for coming to the recording session. It's the last one of this class. It's been a good semester from my perspective, and don't let me forget, one of the goals is to actually have you complete that. It wasn't planned to be on such a light day, so you're going to have to make up for your classmates in some way that way. Homework 2 is due today, and you should be able to do that either today in class or through my Dropbox in the ECE building or the virtual Dropbox online. You have many ways of submitting your homework. The final exam review session is actually this Friday. It's not going to be next week. It's this Friday. That will be in ECE room 530, and it will start at 5:30. And hopefully that works for some of your schedules. The final exam is on a Wednesday, and that will be a week from tomorrow. And so you'll maybe want to set your alarm for a week from now. And maybe you'll be here 30 minutes early. The exam will only start at 1 o'clock. It will be a 2-hour exam, and we'll have a few more pieces of information on that when we get into the goals of today's class. Office hours, the normal ones are still in effect, even though tomorrow is the last day of class. Thursday, I will try to hold office hours from 9 to 11. Don't think something's going to bump that, but even though it's reading day, it seems to be a very busy day. Hopefully not for you. Hopefully you can start reading and preparing for your final exams. That's on Thursday. The following day, the first day of finals, I will hold office hours from 2 to 4, and again, the review session will be shortly thereafter on Friday afternoon at 5:30. That's the plan. If you have any last-minute questions, why is the sign a negative? Hopefully they're just minor by the day of the final exam. I want you to review the material. So what I want to accomplish today are 3 things. One is tell you what to expect on the final in terms of the process, and that should be very consistent with what we've done all semester. We'll go through designing digital filters. We'll use that really as a little bit of a review, but also to show you where you can take the material that you've already learned this semester and how it can be connected with what you already know. We'll turn all integrator block diagrams, hopefully if we get time, into all delay block diagrams. And you can now see that we can easily transition from differential equations to difference equations. And difference equations are very easy to implement on a processor, be that a little PIC, be that some other kind of device. What I want to do now is, and then finally, the other thing that I can't forget, which I keep forgetting, is to hand out the TCE form and have you complete that. The final exam process is that the final is comprehensive and it will be uniformly distributed over the material. It won't be emphasizing the material since the 3rd exam, but the material since the 3rd exam is fair game. Fourier transforms and sampling, and what are these apparent frequencies, or what are these aliased frequencies? What are their values? You're not going to have to change your coordinates. It's still going to be in this room, but your day is going to be different. It's on a Wednesday, and it will be at 1 o'clock. You will be allowed one more sheet of notes, so hopefully you can keep track of all this. You can have the front and back covered with a standard size piece of paper. You can also have a copy of the Laplace transforms, which I believe is on what page? 344 is what I was going to guess, but I didn't know if I should say that or not. But page 344 of your textbook is where that table is found, calculator and a writing instrument or tool. Are there any questions on the final? And I will try to post a topic list, but that's about it, other than the review lecture for the final. Yes? The review is this Friday evening at 5:30 in room ECE 530. I got stuck on 5:30. So try to keep, it's room 530 at 5:30. And that's a PM. Yes, sir. No final sample exams. That's correct. So use your exams that you've been using, and then you'll have to rely on the homeworks since then. No. The question was, will I have office hours next Monday and Tuesday? Unfortunately, I'm not going to be in the office Monday and Tuesday of next week, but I do have them Wednesday, Thursday, and Friday of this week, and Wednesday of next week. And that's all on the front part of the notes. But if you do have questions that don't correlate with the office hours, you can send me an email and we can try to do some exchanging that way, if that is better for you. What I now want to do is talk about filtering, but now from a digital perspective. But I want to use this as really sort of a review, and also to show you how what you've already learned can go a long way in helping you move into a completely new territory, which is the digital realm. And we've already done this a little bit, but now let's do it a little bit further. Suppose somebody wants to build a filter and they have the following specifications. They say it's going to be low pass, have Butterworth pattern, and what does that mean? Butterworth pattern. Maximally flat, and that tells you how they're spread or distributed around the S-plane, doesn't it? When they say Butterworth, now you know the formula for computing the angular separation of those poles. And if you have an even number, you don't have a pole on the real axis. If you have an odd number of poles, you do have that, and then the angle can be appropriately used to locate those pole patterns or those pole locations. Suppose that somebody says, I want the cutoff of that low-pass filter to be at 30 hertz, and I want you to be down 10 dB by the time you get to 70 hertz. And those specifications now should allow you to create a low-pass Butterworth filter with the appropriate cutoff frequency. And what is this third spec allowing you to do? Hopefully. What are you going to get from that third specification? The order of the filter, how sharply you are going to be rolling off. And we know that we're rolling off 20 dB per decade for every order, or 6 dB per octave for every order. And we'll see if we can figure that out. But how far away is 30 or 70 from 30? Pardon? 40 hertz. In terms of decade and octave, it's neither one, is it? But it's a little bit beyond an octave, beyond 30. So it's a little more than a factor of 2. That should help us with our design. Let's now talk about a solution to this. The first thing that we can see is that we can see that, well, I'll call it F sub B. That's what I'm going to call is where I want to block frequencies. I'll say F sub B, that's the blocking frequency. I need to be so far down by that frequency. And I also know my cutoff frequency, F sub C, is 30 hertz. And now I can look and determine their relationship or their ratio. if I look at their ratio, I can see that I'm 7/3. That's the factor. And maybe that's closer to 2 or 4 or 8 than it is to 10. Since that's a little bit bigger than 2, what is a 1 octave give me? That gives me a factor of 2. So this is now a factor of 2 that I'm interested in looking, because that 7/3 is close to 2. Or what does that 7/3 represent? Now I have 7/3 over 2. How many octaves do I have now, really, in that distance between the cutoff and the break frequency? I have 7/6 of an octave. And now I can use that to help me figure out what order of a filter I need, because I know that I have -6 dB per octave and order. I know that I have 7/6 of an octave that I'm spanning between the cutoff frequency and the break frequency. And I want to know what is the N, or the order of my filter. I'm trying to find capital N. And I said that I wanted all of that to be equal to -10. I wanted to be 10 dB after transitioning across a frequency span of 7/6 of an octave. And now I can just do my dimensional analysis. The octaves cancel, the orders cancel, and now I end up with, well, and the 6's actually cancel, don't they? So let me go ahead and just cancel those. And now I'm left with 7N equaling 10. Or I need a filter of order 10/7. But N needs to be an integer, so now I need a second order filter. I've now used the information that I was given in the design specifications. I now know that I have a second order filter. I have a cutoff frequency of 30 Hertz, and I have a Butterworth pattern. Once that I know that Butterworth pattern, I know how the angles, or those poles, are separated in terms of angular units. In this case, my poles are now separated by 90 degrees. The filter order N was even. Which means that I don't have any poles on the real axis. And I'm looking now at this picture. I need to split that 90 degrees equally above and below the real axis. And to get all 4 of those, I would put those other 2 in the right half plane. And I'm now dealing right now with a normalized set of poles, meaning my radial distance away from the origin is this distance of 1. And now I know where my poles need to be. I'm going to retain these poles in the left half plane so that I build up this stable filter. And I know from trigonometry where those poles are located. They're at 45 degrees above the real line. I now have this minus square root of 2 over 2 plus and minus j square root of 2 over 2. Those are my normalized poles. All of this better just sort of be a review, so this should just be very comforting to you, this process of talking our way through this. They're the normalized poles. If I wanted to create the denominator for this filter, I could write it in the form that I like to see it in, s plus the real part squared plus the imaginary part squared. Or if I now multiply all of that out, I end up with this denominator polynomial, and this could be on your note sheet if you wanted. You could have these different filter orders normalized in terms of their representation. If I'm building a low-pass filter, what does the transfer function look like? If that's my denominator, a low-pass filter has what kind of a property in terms of being proper, improper, or strictly proper? Which should it be for a low-pass filter behavior? Strictly proper, because I wanted high frequencies for those poles to dominate, and I need to be rolling off. That means that my numerator is just a 1 in the normalized form. Because I have this radius of 1, this last constant coefficient is always going to be a 1 when I multiply everything out, no matter what the filter order is. What do I do now? So now I have to go back and say, what kind of a bandwidth did I want this low-pass filter to possess? Now it's going to be 1 radian per second. And somebody told me I want the cutoff frequency to actually be at 30 hertz. We can convert that then to radians per second, and now we really need to do this frequency scaling, where our cutoff frequency in radians per second is 2 pi times f sub c, which we said was 30. We're now looking at a cutoff frequency of 60 pi, or a little bit under 200. How do we use that information? If we frequency scale, we're now replacing everywhere we had an S in the normalized filter with a scaled, a frequency scaled S value, S over omega sub C. We now are replacing S with S over omega C. In our case, then, we end up with this low-pass filter having the same structure. It's just now everywhere we had an S, we replace it with S over omega C. And if we multiply by 1, which could be omega C over omega C, let's say omega C squared over omega C squared, we can rewrite that in that form. And this is now the end of our review period, right? You should have been pretty comfortable with that. And if you were wanting to do that, you could actually put those numbers into a MATLAB program and investigate whether you're happy or not with this behavior. In this illustration, the dotted line is the noisy signal, where I had a, let's say, a 10 hertz waveform with 70 hertz noise superimposed on it, with their ratio of amplitudes being 4:1. So I had 1 1/4 for the scaling on the amplitudes, and that produced this blue curve that's dotted. Then I passed it through this second order low-pass filter, and the result is that green curve. And hopefully you can see that there is some filtering going on, that you are getting rid of some of these high-frequency modifications to a pure 10 hertz sine wave. Suppose I'm not happy with that green curve. What would I do? What are some options? You could change the cutoff frequency. How would you change the cutoff frequency? If you wanted to make this more filtered, if you wanted to maybe make that green curve a little bit more sinusoidal or pure sinusoidal, and you were doing it by changing the cutoff frequency, which way would you slide the cutoff frequency in this low-pass filter? To the left, maybe make it a little lower, but that's going to depend, isn't it, on what somebody tells you the frequency content of your signal is. Here I used a 10 hertz waveform. If they said that's about as high as you're going to get in frequency signal, then if you put your cutoff at 10, what do you know is going to happen to the amplitude? It's going to be reduced by 3 dB, isn't it? And that's a half power point, but that's now a factor of 0.7. So you are going to get a 70% reduction in the amplitude, but you might make the waveform a little smoother. Now you could also change the order of the filter, couldn't you? You could say, I want to really be much lower than 10 dB by the time I get to 70. Because 10 dB isn't that much. 20 dB is 0.1. So now you're passing, if it was a 20 dB reduction, it would be a tenth of what you started with. Now we're not even that far. We're at 10 dB. So you might say, well, let me double my filter order and get a fourth order filter. There's a lot of things that you can now do to enhance or modify the results that you're seeing. And that's actually what's happening over at Design Day. Somebody actually said, oh, Dr. Tharp, I had to do a Butterworth filter. So there is stuff that you can use from your material that you're learning, not only in this class, but in other classes, hopefully. What I want to do now is take this into another domain. This is the S domain, and that's associated with continuous time signals or analog waveforms. A lot of times we're playing with strings of numbers, digital numbers, or a discrete time. We sample the time axis. Let's see if we can now build a filter that no longer is a function of S, but now is a function of Z. And you'll now have a Z transform instead of a Laplace transform. Or an H of S, you're going to have an H of Z. Let's see if we can now talk our way through a new concept based on what we've already built as far as tools in this class. Let's start talking about a discrete equivalent, meaning you now know how to build up any kind of low-pass filter you want, Butterworth, Wise. Now somebody goes, I don't want an analog filter. I don't want op amps, R's, and C's. I want you to put this on a little device and use it somewhere else. I want you to program this filter into some code. You now want to, oh, I've got a 10th order Butterworth filter in the analog setting. Now let's see if we can turn that into a discrete time filter. And then we can put it into our code if we want. What we have to begin with is that. That's how we started the semester, wasn't it? An input going through a system, generating another signal as the output. What we want to do is we actually want to replace this with, now our frequency domain is not the S domain, it's now the Z domain. We want to replace the blue diagram with the black. We want to build an H of Z. And there's a lot of different ways that you can do this. And they could be classified as discrete equivalents. And you might see this in a 429, a digital signal processing class. You might see this in a digital controls class, a 442. One approach to obtain a discrete equivalent is to do it by means of numerical integration. All that means is that you're integrating numerically. You're now chopping up this integral problem into little discrete slivers, which is how you started your calculus. You said, how do I approximate the area under this curve? Well, I just start creating little slivers, and then I add those up. So we're not doing anything differently than what you did when you were playing with blocks growing up. You were stacking blocks together. Now you're stacking slivers together to do numerical integration. Now we can throw in some more terminology, and you can impress your friends that didn't make it to class. You can say, oh yeah, we talked about the trapezoidal approach of numerical integration. And they're going to go, what? Yeah, it's going to be on the final. See what you missed? Oh yeah, and the recording didn't work. Can I see your notes? I didn't take notes. It's all up here, right? Wow. Have you heard of the trapezoidal approach? Or maybe you've heard of a bilinear transformation. That's what we're doing. We're replacing S's now with some combination of Z's. Just like we replaced in frequency scaling, we replaced S with S over omega C. Now we're going to replace S's with some combination of Z's. And the combination is going to be based on this trapezoidal approach, or some people call it a bilinear transformation. Here's what we're doing pictorially. I like to sort of see pictures. Here's time. And let's say that somebody gives you a curve x of t, and that's like our input. And then they say, you know what, I want you to find the area underneath that curve. Where the area now underneath that curve is going to be y of t. We're just integrating. When we find the area under a curve, we're integrating. But now, what we want to do is we want to change this continuous time problem into a discrete problem. And the way that we do that is we start to chop it up. We say, oh, here is a time t, and here is a time t minus capital T, meaning the distance between these is a sample period, capital T. And if I go up here to that particular value, this would be x of t, or I'm going to actually replace t with some discrete combination of the sample periods, little n, capital T. This point would then be the value of our input, x, at time n t. Maybe that's 100 sample periods into the future. Little n would be 100. Maybe capital T is a millisecond. That's 0.001. This is now 100 milliseconds into the time horizon of this integration problem. This particular point would be x of, if we said nt minus t, where little t is nt. So this is what I'm going to call x of nt. This entire red piece would be the area under the curve up to time t. But what's the area under the curve up to time t minus cap t, little t minus cap t? If I said, what is this area that's now green? That's y of nt minus t, isn't it? The green is now y of nt minus t. To produce y of t, the area under the curve one sample period into the future beyond nt minus t, I simply need to add in this little area. And how I approximate this area determines the numerical integration approach. The trapezoidal technique is going to now just create this area as a trapezoid. Is that making sense? I could do a backward approximation where I use x of t and just go straight across. I could use a forward where I just go straight across from x of nt minus t. I'm actually going to perform a trapezoidal approximation for that area, meaning now y of nt, the total area up to time little t, is made up of y of nt minus t plus that delta area. And the delta area, I'm going to now let that be equal to the area of that trapezoid. What's the area of a trapezoid? It's the width and the average of the two sides. Meaning this delta area is now going to be the area of wake me up. That's the average of my two heights times capital T. And I now have a difference equation relationship between the input, which was the x, and the output, which was the y. This is now a numerical integration approach based on a trapezoidal area for the area under that curve. And now as I increase my sample period, little n, I just get more and more of the area. Is that making any sense? What do we want to do? We want to figure out, how do I replace s with something in z? If we now think of this as, let me it really doesn't matter how I define my time. What if I said, what if I just scale everything, shift everything by 1 unit of time? I'm going to still have this same functional relationship. I've just changed the argument by capital T in every one of those arguments. It's still the same in terms of functional form. What if I now recalled, did I ever talk about Z being an operator? No. Did I ever talk about S being an operator? S times X of S is like doing what in the time domain? Differentiation. 1 over S times X is like doing integration. So you're familiar with, if I wanted y of s to be the Laplace transform of the integral of x, that would be what I would have. This is now this is kind of an abuse of notation, but that's like an integration in the S domain. 1 over S is like an integrator. So if we had an all-integrator block diagram and somebody said, oh, draw that in the frequency domain, you would replace all of those elongated S's with a 1 over S. You would now have a S domain or a frequency domain block diagram. What we want to do is see if we can relate this difference equation to something that relates y of z and x of z. In the discrete setting, z as an operator a multiplication by z is like an advance of 1 unit. Meaning y of n plus 1 capital T is going to be like what operation? That's an advance of 1, and that's just a multiplication by z in the frequency domain. This little y now on the left-hand side gives me z times capital Y of z equaling capital Y of z plus t over 2 x, well, that's z, x of z plus x of z. Meaning we had an advance of 1, that corresponds to a multiplication by z in the frequency domain. We had another advance of 1 in the x, and that's z times x of z. Let's factor out some of those y's and z's. We now have a z minus 1 y of z is equal to 2 over t z plus 1 x of z. Or y of z over x of z becomes t over 2 z plus 1 over z minus 1. Or maybe I should keep that x of z on the other side to be consistent with what I had just done up above. What am I doing now? I did in the discrete time setting, this equation corresponded to an integration. In the frequency domain, this is now the relationship of that integration. I now have this is similar in structure to the analog form of 1 over s. Meaning now 1 over s is equivalent to this combination of z's. And this gives me my strategy. Now if I set s, or replace s with what this needs to be equal to in the z domain, I've now found a way to go from h of s to h of z. What I want to do now is replace s with that expression. Obviously, I have 1 over s being equal to that expression, so I now need to invert everything. And if I replace s everywhere in my h of s with that 2 over cap t z minus 1 over z plus 1, I'm now going to obtain my transfer function in terms of the z variable, capital H of z. What is capital T? If I write that a little bit differently, I can now say that I'm going to build up this h of z by starting with h of s, that's my analog filter, and I'm going to replace s with this 2 over t z minus 1 over z plus 1. This gives me a strategy for building a digital filter or designing a digital filter from an analog filter. What did we have before? We had our analog filter. That was this omega c squared over. Now we had an s squared. Well, that's just 2 over t, z minus 1 over z plus 1, quantity squared, plus the square root of 2 omega c s, but we're replacing all of those s's with this bilinear transformation of z, plus omega sub c squared. And we knew that our omega sub c was 60 pi. And now all you have to do is the algebra to create a transfer function in z. But before we do that, what would we pick for capital T? We have this. This is going back to our review. What would we pick for capital T? If somebody's now doing a design, how do we pick capital T? What is T? We're now trying to implement a digital filter. T is now trying to sample this system that is producing a low-pass filter effect. And what do we know about that low-pass filter, the capital H of S? We know the cutoff frequency, don't we? That's sort of the important frequency of interest. Everything beyond that, we're going to try to get rid of. They're still going to be there, but we want to start neglecting frequencies beyond omega sub c. If that's what we want to concentrate on, how fast do we think we should sample? If that's our sort of frequency of interest, now I'm going to introduce a new frequency. Let me call it the sampling frequency, f sub s. And that's going to be just a rule of thumb, a quick way of picking that. We could just say, I need that to be 30 times my cutoff frequency, a factor of 30, bigger. Our sampling frequency now needs to be 30 f sub c or bigger. F sub c was already 30, wasn't it? So this is now 900. Well, that's maybe a not so neat number. Let's just go beyond that a little bit and make it 1,000. That's now our sampling frequency, f sub s, is 1,000 hertz, which the sampling period, capital T, is the reciprocal of 1,000. Or we're now sampling at every millisecond. I'm sure you're wondering what h of z looks like. It's now, and I did this with MATLAB. I didn't do this by hand. But I plugged in the appropriate 10 to the minus 3 for capital T, and I already had omega sub c, and I had my z's floating around. MATLAB now gave me 0.0078 z squared plus 0.0156 z plus 0.0078 upstairs. Downstairs, I have a z squared minus 1.7355z plus 0.7666. And that's now a discrete time low-pass filter that has a cutoff frequency of 30 hertz. And it's based on a sampling period of 1 millisecond. You've now designed a digital filter. And this, graphically, is consistent with what you've been doing in the analog domain. You now take this input signal, run it through this digital filter, and produce an output. But all I'm saying now is that's equivalent to just doing some difference equation manipulation. You give me an input, I'll take it, and I'll put it into the filter. The filter will take it, it will scale it, it will add it in with previous outputs and inputs, and spit out an output. And that output now will be a low-pass filtered version of X. And it's all doing it with addition and scaling, amplification of numbers bigger or smaller than 1. What's a way of looking at this? You could look at this, y of z over x of z is now just a second order numerator, and let me just say that I'm tired of writing all of those coefficients. Let me collapse those down into b's, and these b's won't sting you. Aren't you glad this is the last lecture? There's our b's, b2, b1, and b0. Then we have, let's say, a's down below. And that denominator was monic, meaning the leading coefficient of that highest power of z was 1. We normalized that to be 1. I can now turn this into a difference equation. Just like I could turn a transfer function in the S domain into a differential equation. It's the same process. I cross multiply. I can now say, oh, I have a z squared plus a1z plus an a sub 0 times y of z equaling a b sub 2 z squared plus a b1z plus a b sub 0 x of z. What's that going to produce? Remember what a z does in the time domain? This is like an advance of 1. A z squared is like an advance of 2. If I now inverse z transform this, so now what can you tell your friends that weren't here? Oh yeah, we did some bilinear transformations on a low-pass filter. We did some digital filtering. We also did some inverse z transforms, came up with some difference equations, went into an all delay block diagram, and it's all on the final. Hey, wake up, he's talking about the final. What do we have? If we now take this into the time domain, we now have y of n plus 2. I'm going to drop the capital T. This is n plus 2 sample periods, plus an a1 y of n plus 1, plus an a sub 0 y of n. And that's equal to a b sub 2 x of n plus 2 plus a b1 x of n plus 1 plus a b sub 0 x of n. Now I have a second order it's a linear, I'm just going to say difference equation. Now we have a second order difference equation, just like we've had a second order differential equation. And what's the second order? Now I have a difference of 2 in my argument of the y variable. If I took the z transform and looked at the denominator, my denominator is second order in z. Second order, z squared. This should start to look, well, sort of like that integrator equation or that differential equation. What if I now start introducing delays? What if I now solve for this highest sort of argument of y of n plus 2? What if I pushed everything else on the other side of the equality sign, and then I started delaying the entire equation until I ended up with y of n on the left? Because if I delay y of n plus 2, if I delay this by 1, what's going to result? Y of n plus 1. If I delay it again, I'm going to end up with y of n. And that's going to allow me to build up a block diagram. Did everybody bring their seat belts today? We've done an entire semester now of signal processing in under an hour, right? Aren't you impressed? So let's now go into a block diagram. You can now do this on your capstone next year. You could do some signal processing. That's what somebody said. Oh, Dr. Tharp, I used 340 because I needed it to do my signal processing in my capstone project. What if I now delay it once and I've pushed everything else to the other side? Meaning now I have y of n plus 1 is equal to b sub 2 x of n plus 1, and I'm going to start collecting all of my terms that are of the same argument in the b's and the x's. I then have a b1 x of n minus an a1 y of n. But then I have, if I delay this term and that term. I don't want to go anywhere below y of n and x of n. I need to keep those. That's what I'm assuming I have access to, my input now and my output now. I'm going to put a delay operator in front of those, meaning I can now replace those or rewrite those as saying plus a delay of b sub 0 x of n minus a sub 0 y of n. All of that's on the right-hand side. If I delay again, now I end up with y of n, b sub 2 x of n, plus a delay of b1 x of n minus a1 y of n. But I now need to put inside that this piece that I've already delayed. Notice that I haven't closed up my curly brace on the right. This is still b sub 0 x of n minus a sub 0 y of n. And now I'm in a position to close up that second delay. Meaning these two terms are going to be delayed twice in the process of creating my present output y. Now I can sketch my block diagram, and I can build that by simply, what do I have here? I just have x of n's and y of n's with some delays, some coefficients, and some adding and subtracting. Let me create y of n out of all of those pieces. Now I can build up my block diagram. And what are we doing? We're just low-pass filtering, aren't we? So here's x of n. And let's say that I have here y of n. But y of n, if I went back up there, that was just b sub 2 x of n. And the output of that red delay. And I'm going to now just make this, call this a new signal coming out of a delay block. And what feeds that delay block? Well, internal to that delay block, which is inside the red curly brace, is b1x minus a1y plus the output of another delay block. Meaning I can now go back here and say, oh, coming in here is a b1 times x, a minus a1 times y, and the output of another delay block. Where the input of that delay block is this black square bracketed piece, which is just a linear combination of the input and the output. And if I do that, I can go back here and I can say, oh, the input here to this delay block is just a minus a sub 0 times the output. Whoops. I need to gain that. And now I have a block diagram that's an all delay block diagram. I have two delays, and I inject an input x, and out comes a filtered version y. And you can actually now build a state space representation from this by labeling the outputs of these delay blocks as your state variables. Just like we labeled the outputs of our integrators as state variables before, now we do the same analogous process. We're just building up discrete time state space representations. What's this signal going to be? Coming into the rightmost unit delay block. What would this signal be called if the output is Q sub 1 of n? This guy right here is going to be Q sub 1 of n plus 1, isn't it? And this point right here is Q sub 2 of n plus 1. And from this block diagram, you can now see that what's y of n? Y of n is just a linear combination of the input, b sub 2x, plus Q sub 1 of n. And that's your output equation. And a linear combination of the states and the input. And you can also define your Q's one time step into the future. You can say Q sub 1 of n plus 1 is now minus a1y plus b1x plus Q sub 1 of n. But we need to make sure that this gets rid of the y. And then we have our state equation in terms of states. Q1, maybe a Q2, in this case not. Oh yes, what was this? That was not Q1. Keep me awake. What was that? That's this guy right here, isn't it? That should be a Q sub 2. So that now Q sub 1 of n plus 1 is minus a1 Q sub 1 of n plus Q sub 2 of n plus b1 minus b sub 2 a1 x of n. And that's now your first of your two state equations in your state variables. And you could now build up this discrete time state space representation. Which, let me just give you the answer in the back of the book. You can now say that you have a state space representation. Here's A1, here's A sub 0, there's a 1, 0, here's a Q sub 1 of n, a Q sub 2 of n, plus a B sub 1 minus A1 B2, and this is now times x of n, and this is a B0 minus A sub 0 B2, where y of n is Q1 of n, no Q sub 2, plus B sub 2 x of n. And now you have a discrete time state space representation that's second order. And you have your system matrix, input matrix, output matrix, direct feed-through matrix. And this structure looks consistent with what you've seen for the continuous time state space representation. Questions on that? Now you're ready for the final, right? You've taken a review of a low-pass filter and you've now learned how that could be used in subsequent classes based on what you know from your material from this class in 340. Are there questions? You're afraid to ask. I don't blame you because it might be on the final, right? This digital filter stuff won't be on the final, but the review part leading up to it, you can expect. The analog filter design, how to design those filters. Yes? Yes, so what does a low-pass filter do? You're really, if you looked at a very simplistic low-pass filter, you're averaging. And that's what this is doing. This numerical approximation to your analog low-pass filter, it's taking your input, this noisy signal, it's scaling that in a certain way based on your bandwidth and your order of your filter. That's going to give you the B's and the A's. And you just combine that with previous values of your output and present values of your input and delayed versions of those, and it filters it. And it's basically doing an average, a more sophisticated average. But that's what's happening. And sometimes this block diagram makes it seem a little more clear. Sometimes maybe it's more clear to just play with this difference equation or see the difference equation. Now I just have to have a couple of memory locations for previous outputs, a couple of memory locations for previous inputs, and now I can just turn the crank in this algorithm. Now you have an algorithm, a numerical algorithm for doing low-pass filtering. I'm going to stop at that point.